Alrighty, so in this video we talk about matrix norms. So last video we talked about vector norms. You'll see that the definition of a matrix norm is pretty much the same thing, right? So what are the four properties that a matrix norm has to satisfy? So it's a function from the set of m by n matrices to the non-negative real numbers. Satisfies what? For all matrices. So I'm going to refer to A as a matrix, right? You can think of A as a element in a vector space, and you could call A a vector, but that will be confusing when we talk about, say, matrix vector products or matrices applied to vectors and whatnot. But you can abstractly think of a matrix as an element of a vector space. But I'm just going to use the term matrix to keep it kind of distinct. So for all A in the set of m by n matrices, what has to be true is that the norm of A has to be greater than or equal to 0. Again, so you'll see that these are basically exactly the same things as a vector norm. And this is because you can think of matrices as vectors in a vector space. The norm of A is equal to 0 if and only if A is equal to the 0 matrix, which sometimes I'll write as subscripted by the dimensions, so it's clear like how many zeros are we talking about and what shape. Right, so the third property, you could probably guess, again, it's going to be the scalar property. So alpha, for any constant alpha, times A, this has to be equal to the magnitude of alpha times the norm of A. So we can pull scalars out as we could for vector norms, and this has to be true for all m by n matrices, and for all scalars alpha, for all real numbers alpha. And then finally, the fourth property is that I need the triangle inequality to be satisfied by the matrix norm. So if I take the sum of two matrices and I take their norm, this has to be less than or equal to the norm of A plus the norm of B. Obviously, for all A and B, all matrices A and B of size m by n. So that's your definition of a matrix norm. So next we're going to talk about induced matrix norms. So this is I can kind of think of these as a factory for generating matrix norms out of vector norms. Right? So if I have a vector norm on Rn, I could define an induced or subordinate matrix norm on the set of m by n matrices using the vector norm. Right, so if I have a vector norm, I can build a matrix norm. And the way that you do this is I define the norm. So if given my vector norm, again, I'm subscripting with this A just to note it could be any vector norm. The matrix norm induced by that vector norm is equal to the maximum taken over all non-zero vectors x of this ratio ax, the norm of ax, divided by the norm of x. But then this is also equal to the maximum taken over all vectors of a norm equal to 1 of just ax, its a norm. So this is the definition. These are you see that these are actually different. These are two different statements, right? So I'm defining it as being equal to either of these. So you might ask, like, why are these the same, or are these equivalent? So you can check that yes, they are. So if we think about this, the maximum over all vectors, all non-zero vectors of ax, its a norm. Well, in the denominator, the norm of x, the a norm of x, is just a scalar. So using the scalar property that has to be satisfied by the vector norm, which is also what's appearing on the top, right? Because I have a matrix times a vector. So the operator on the top is a vector norm. So this has to be equal to the maximum still of all non-zero vectors x of this expression. So here what I've done is I've absorbed, I'll put 1 over the a norm of x times x. I've just pulled the that constant of 1, that scalar of 1 over the norm of x all the way into the expression above, which I'm allowed to do. And then what do I look at here? So here I wind up with this expression that's x divided by, or x times 1 over the, x times the constant that's 1 over the norm, the a norm of x. And so what do I get? So I can always check that the a norm of this vector here, its a norm is always equal to 1, just by definition. And so what this means is that I can replace these constraints that I have, both the constraint here and what shows up here. I can just replace this whole thing with the max of, I'll just use a different vector, y, all vectors y with a norm equal to 1. Because no matter what x I had over here, it had to have a norm 1. And then I can just replace it with it here. So I get a times y, then the a norm. Sorry, there's a lot of a's, but hopefully you see what I'm saying. So that's why these expressions are the same. But yes, so you can check that the induced matrix norm satisfies all of the properties of a matrix norm that I gave you on the previous slide. So this is one way to build a matrix norm, is to take any vector norm and then consider the induced matrix norm induced by that vector norm. So we just talked about induced matrix norms, and so you might ask what matrix norms are induced by the vector p norms that we talked about in the last video. And so here I'm going to let A be an m by n matrix. I'm going to kind of just partition its columns, right? So A1 through AN are the ith column vectors of A. And so, right, so if I consider the induced 1 norm, matrix 1 norm now, what is this equal to? So by the definition that I gave you for the induced matrix norms, that's how you would arrive at this line. So I've just plugged into the definition. So I need to maximize the 1 norm of AX over all vectors of 1 norm equal to 1. So of a unit 1 norm. I'm sorry, there's a lot of 1s, but it's the 1 norm. So, and so that basically I'm playing that same game for all of these, for these first 2 columns, is I'm just saying, okay, what is the induced 2 norm? What is the induced matrix 2 norm? What is the induced matrix infinity norm? Right, and so that's how you arrive at these statements, is I'm just plugging into the definition. But kind of the cool thing is that you can actually explicitly calculate the values of these, or like of what is the maximum value in these expressions. You can calculate these explicitly. Some of them involve some tricks to figure out these expressions, but that's essentially what's showing up here on these last 2 columns here, right? So these are equivalent expressions for the matrix, the induced matrix P norms of P is equal to 1, 2, and infinity, right? So let's just kind of run through what they say. So the first line here says that the matrix 1 norm is equal to, if I maximize the column sum, if I take the absolute value of all the entries and then I look at the maximum column sum, so let me write max, I'm going to call it abs column sum, just so you can think about it like that, right? And so I can write it like this, which is saying I look at all the column vectors A, J, I take their 1 norm, and then I take the maximum of that 1 norm over all of the columns, and that's how I get the matrix. So you could show that just from the definition of the induced matrix 1 norm, that this is equal to the max absolute column sum, right? And so kind of the same idea. This is a cool one that you'll see, I think, on the problem set, is that the matrix 2 norm is actually just equal to the maximum singular value of A. So if you think about the SVD of A, and you look at the largest singular value, that's just equal to the 2 norm of A. And kind of how there's this equivalency, or you could always think about the singular values as the eigenvalues of this gram matrix A transpose A. You could also write that the 2 norm was equal to the square root of the largest eigenvalues of A transpose A, right? And so I'll just note that this the 2 norm, the induced matrix 2 norm, is also known as the spectral norm of a matrix A. And then finally, this infinity norm, or the induced matrix infinity norm, this is equal to, it's kind of similar to the one norm that we saw here, except now what we're doing is we're looking in the rows, right? So this is going to be the max abs row sum, the maximum absolute row sum. And then you can kind of succinctly write this as actually the one norm of A transpose. This is another quick way to write it, what it's equal to. So if you could calculate the one norm, then you can calculate the infinity norm by transposing the matrix first. Because you transpose the rows becomes the columns. Okay. One kind of important property is that for any induced matrix norm, so not just the induced P norms, but any, I'll write any induced norm, by the definition of the induced norm, satisfies AX is less than or equal to A, the norm of A, times the norm of X. So here the norms are taken to be, I'm sorry, I just realized you can't see that. Let me move this here. Yep. So any induced norm satisfies this inequality. So if I take the induced, if I take the vector norm of AX, this has to be less than or equal to the induced matrix norm by that vector norm applied to A times the vector norm. And this has to be true for all X. Let me write for all X, so you have this. Okay, so that's an important property to keep in mind for induced matrix norms. So a quick comment I wanted to make for you is that there's also something called the spectral radius. And so what the spectral radius is given a square matrix, so it has its eigenvalues. You define that it's the spectral radius of A, so you use rho of A, is commonly how you see it. This is equal to the, in absolute value, the maximum eigenvalue. So I look at all the eigenvalues, and then I take their absolute value, and then I ask what's the largest one, or the magnitude if you had complex eigenvalues, any complex eigenvalues. So I just put this warning symbol to tell you that you should not confuse this with the spectral norm. So I told you that the spectral norm was equal to the 2 norm of A, that this was the spectral norm. But this is different than the spectral radius. It's not the same thing. And that actually in general, the spectral radius is not a norm, which you can prove that it would not satisfy all the properties of a matrix norm. So I just wanted to put that on your radar. So the next big property of matrix norms to consider is whether or not they're submultiplicative. And so what this means is that if I take the product of the two matrices A and B, and I take their matrix norm, whatever matrix norm I'm considering, is this true? So in general, this inequality is not true, right? So I'm asking, can I bound the matrix norm of AB by the product of the two matrix norms of A and B? In general, this is not true. So that's why I put this warning symbol again for you, just to warn you. But kind of the cool fact, and this comes from that property earlier, that the norm of AX is less than or equal to the norm of A times the norm of X, if it's an induced vector norm, or induced matrix norm. What is true is that for all induced matrix norms, this is true. It is true. So what we say is that all induced matrix norms are submultiplicative. I mean, how do you see this? We can quickly kind of just go through it. So if I look at and here I'm going to consider again the A norm, the A vector norm, or the induced A matrix norm now. Well, this is going to be equal to, by the definition of an induced matrix norm, this is the maximum over all vectors of A norm equal to 1. Of A, B, X, it's A norm, just by definition. And then what can I say? I'm just going to insert some parentheses because I'm allowed to do that. We'll say this is equal to the maximum of all vectors of A norm 1 of A, B, X. Okay? And so now what am I going to apply is that inequality that I told you is satisfied by all induced matrix norms. This is less than or equal to the maximum taken over all vectors of A norm 1 of the A induced matrix A norm of A times the vector A norm of Bx. So I'm just using that property of induced matrix norms. What I can do is I can then pull out completely this A, right? I can pull out the A entirely because it's just a scalar at this point. It doesn't depend on X. So this gives me, this is the A norm, induced matrix A norm of A. Sorry, there's still a lot of A's. Times the maximum of all vectors of A norm 1. Take the maximum of Bx, its A norm. And then actually this last part is just the definition of the induced matrix norm for the A vector norm, right? So what I see is that this is actually just equal to A, the induced A norm of A times the induced B norm, sorry, the induced A norm of B, right? So that proves why for all induced matrix norms, they're all submultiplicative. All right, so now let's talk about an example of a matrix norm that is not an induced matrix norm. Right, so we talked about induced matrix norms, how you can build those out of vector norms. But now this is an example of a norm that we did not build or is not built out of a vector norm. So the idea of the Frobenius norm is what are we going to do? We're going to take our vector, or our matrix A, we're going to write it again kind of as this column vector notation, right? So the sequence of its column vectors. We're just going to stack them into one big column vector. Right, so all I did is I just said, just stack A1 on top of A2 all the way down on top of AN. And what we're going to get is we're going to get one big vector that lives in our m by, not m by n anymore, but n times n. Right, so I basically just flattened. So if you're familiar with, say, NumPy or MATLAB or any of these array libraries for computing, we're flattening the two-dimensional array into just a one-dimensional vector. And then I could say, well, let's take its 2 norm. Let's just take the 2 norm of the flattened vector. And that's what the Frobenius norm is. So the Frobenius norm, we subscript it by F just for Frobenius. So the Frobenius norm, you can also define it like this. So you'll see that this is just exactly the 2 norm, the definition of the matrix, the vector 2 norm applied to this kind of flattened version of the matrix A. One kind of cool property, which you flatten it, and you would think you would lose a lot of kind of the structure that's in the matrix, but actually you can show that the Frobenius norm is equal to the square root of the trace of A transpose A. And so I've actually given this to you. This is on the problem set. So I think I have 1 or 2 problems where you walk through arriving at this formula for the Frobenius norm. I think it's kind of a cool process. It uses properties of orthogonal matrices and the trace trick, which you'll learn, the cyclic property of the trace. Right. So kind of some history on the Frobenius norm. I'll just say here, it was first used by Wedderburn in 1925, but then it was really named and considered more greatly, also by Wedderburn in 1934. So kind of the last thing I'll say about the Frobenius norm is that, right, so I've put a note down here for you. It's also submultiplicative. You could show that it is, but it's not because it's an induced matrix norm, because it's not an induced matrix norm. So it coincidentally also is submultiplicative, but not because it's an induced norm, because it's not. So just keep that in mind. So basically, in this class, we're going to be considering, really the only matrix norms we ever consider will be the Frobenius norm or any of the induced matrix P norms. So for the intents and purposes of our class, all matrix norms are submultiplicative, but there are matrix norms that aren't. So just know that property, or know that fact. Okay, so the last thing we're going to talk about, kind of like we did for vector norms, we're going to talk about the equivalence of matrix norms. What is the definition of a matrix norm? I mean, it's essentially the same thing as we defined for a vector norm. We say that two matrix norms, so now here I'm calling a matrix norm A, subscripted by A, and a matrix norm B. We say that these two matrix norms are equivalent if there exists constants C1 and C2, positive constants, such that I can lower bound and upper bound the A norm by some multiple of the B norm from above and below. And this holds for all m by n matrices A. And so again, one fact you can prove is that, like it was for the vector norm case, for all matrix norms, any two matrix norms that you come across are equivalent in finite dimensions, because we have our matrices that have finite dimensions. So this is true. And so there's this nice chart that exists that kind of tells you some upper and lower bounds, the relationships between the different norms that we've talked about in this video. So here what this table is I'm saying, okay, for any value of p, I consider the p norm of A, and I want to upper bound it by some constant times the q norm of A. And so what this table is giving you is what are those constants. So how would I read this? It would tell me that, okay, the A norm, the infinity norm of A. So here I'm going to say P is equal to infinity, and say I want to get it bound in terms of the Frobenius norm. So this would mean that this is less than or equal to, all right, so I look at the column for F, and this tells me this would be, so P is equal to infinity, and Q is equal to F. This would be square root n times the Frobenius norm of A. All right, so this table gives you bounds. And on the problem set, I'm going to ask you to prove some of these bounds. I think I'm going to ask you to prove the equivalency of two sets of matrix norms. So you can look forward to working on that problem. But yep, so that wraps up this video on matrix norms.